Thank you, Jerry, for asking me to speak about this, or actually I volunteered, and thank you for letting me speak, I should say. Um, I am basically going to give a talk on work that spans back quite a bit in time, and it's going to look at some of the early work that was done on LiMO2, stoichiometric LiMO2 type of compounds, where M is a transition metal. And these compounds typically are fairly good as cathode materials for batteries, and that's kind of been one of the leading interests in them in the last 2 decades. And of course, there are other interests in these types of compounds as well, because the alkali ions can essentially be titrated in and out of compounds, either chemically or, as we later found with in the battery cases, we can essentially use the working of the battery to control the stoichiometry of lithium in these compounds fairly accurately. And in doing so, we can change the intrinsic properties of the compounds themselves. And so there's a lot of fundamental physics and chemistry that's going on that can be triggered essentially by the amount of alkali ions present. And so as a playground for studying materials properties changes or structure property relationships, these cathode materials are very interesting. So Delafossite in the title refers to basically a category of these compounds which happen to be layered, and the common battery material that you will have heard of is lithium cobalt oxide, but there are also other sister compounds that are being used in batteries. And then of course there are some compounds in which the transition metals are probably too passive or too heavy to be used effectively as battery compounds, but they work for electrochemical intercalation and deintercalation of lithium and or sodium in some cases. But I'm going to focus on the lithium MO2 Delafoscites, particularly 2 case studies, one with the so-called NMC, the nickel manganese cobalt oxide, and the lithium cobalt oxide. The other part of the title, which refers to the soft and hard X-ray work, essentially I'll be mainly presenting our work, but I want to acknowledge at the outset that even though we did some of the work, there were lots of other people who were also doing the work. Our focus was on trying to do as much on the soft X-ray side as well. And so that is kind of the one thing that I will point out as especially on the Operando side, where we tried to do some innovative things at the beginning, and that yielded some results and confirmed some of the results that others had found in ex-situ studies. So with that, I'll just continue. I should mention one more thing, and that is in the title. There's magnetic properties. So what I'll try to do is tie some of the electronic structure and atomic structure material that we measured in our materials with some nominal understanding of what's happening with magnetic transitions in these cases. So some relevant papers. So here are some from my group or people that I work with. So this spans, as you can see, back to 2005 with the paper on the upper left. That paper is actually looking at only the hard X-ray, that is cobalt K-edge under operating conditions for lithium cobalt oxide, and it happened to be a thin film battery, which was kind of incidental in this case. But we basically were looking at the solid state reaction, and it wouldn't have made a big difference if it was a liquid electrolyte battery, a pouch type of battery, or a more traditional liquid electrolyte battery. It would have essentially had the same solid state reaction. So some of the findings from that paper are essentially relevant to lithium cobalt oxide batteries in general, and not just for thin films. And then we did much later some work with NMC compounds, the lithium, nickel, manganese, cobalt, and then that led to a couple of papers, and later was followed up with another work on another sister compound, lithium niobate, and that where we focused on the oxygen measurements in situ. So for some of you eagle-eyed viewers, you might recognize this name, Stanley Whittingham. He's well known in the battery community, and there he is in the lab and pretending to be doing something. And below that is a picture of him at some kind of an official ceremony with a white tie. Don't know what that might be. Moving on to the next important paper I would like to reference is one that was contemporaneous with the lithium cobalt oxide paper that we had published on the thin film batteries. And this one is basically focused on the NMC and the people that are involved. I wanted to kind of acknowledge some of these people. I remember them very fondly. I know them and work with some of them, but I remember some of them fondly. So let me just acknowledge the upper right corner. We have the original, and then Molly can correct me if I'm wrong, but this is the original battery group at the chemistry department at Brookhaven lab, together with Dan Fisher. And on the left there, Dan Fisher is from the Inst group. He was my boss for a while. He is, and they're all in front of the U7A beamline at Brookhaven National Lab. And in that picture, you see Wanso Bune, you see Jim McBreen, and you see Cheng, and they're all from that chemistry group. The person who's missing from that picture is Mali Balasubramanian, who's moderating this talk. So he's pictured below here. So that paper actually is a very, very good paper, which did soft and hard X-ray work on NMC compounds. And it was Ex-situ for the soft X-ray side, but they were seeing the effects that we later also saw when we did the Operando studies. And so it's essentially confirming that those effects persist even when you take the battery apart. Just to quickly use a schematic. I know this is a X-ray, you guys are X-ray fluent people, X-ray spectroscopy fluent audience here, and so I won't get into too much of the fundamental basics here, which you've all heard in other talks.
Faisal.
Yes, Molly.
Can you hear me?
Yes, I can hear you. Hello? Was there a problem?
I think maybe Molly's having internet problems.
Oh,
that's
okay.
all right. You should
Okay.
continue.
Okay, all right. Okay. So using the schematic, we can essentially divide up why you may want to do soft and hard X-ray work. If you look at these 3D transition metal oxides. Of course, you may be interested in the D electronic structure, the 3D electronic structure of the transition metals, which you can access with high cross-section and low energy and high energy resolution, and in such a way that you could actually do an accounting of the number of electrons present in the D structure. And you would do that under a kind of a dipole transition from the P states. And so you would need soft X-rays for that. So P to D transition would be allowed in the soft X-ray side. On the hard X-ray side, you can essentially get to the fully empty states. However, the SP type states for the transition metals. However, and so they may not be chemically as relevant, but you are able to get large bandwidths of large ranges of energy over which you can do the extended structure measurements, which you are not afforded in the soft X-ray regime. And in this case, we also have oxygen as a participant, and so for accessing the oxygen electronic structure, you obviously need soft X-rays for that. A caution that others have already spoken to in previous talks, and it's not the big focus for my talk, but just wanted to point out that what you see in the Zane's features are interconnected. There's a lot of coupling going on between the bond length, the charge on the central atom, and the ligand, as well as the point group symmetry. And so you have to be cognizant of this fact before you start overinterpreting your data. One quick example, this is a slide I borrowed from Grant Bunker, where he did just some simple models of MnO2 MnO4 planar clusters, where you see what appears to be an energy shift, and it's actually directly from the interatomic bond, the shifts in the changes in the interatomic bond distance. So once you do the 1/r² correction, that disappears. So that's seen here. I just wanted to point out that these kinds of the work that I'll be showing is sometimes very tedious, especially in the soft X-ray side, but I had the fortune of working with some students who are quite creative with their time in between experiments. And here's one student who decided to draw a picture of Cyclops, I believe, one of the X-Men, replacing the synchrotron source and essentially providing the X-ray, in this case, I guess X-rays necessary for the experiment. Unfortunately, Cyclops doesn't know his own power, the limitations of his power, and so he's blasted through the beam stopper there. Okay, let's start with the case study of the NMC compound. So you can, the advantage of designing one battery and being able to do things with operational control of that one battery is that you can go to the multiple edges and you can essentially then collect data as a function of the electrochemical state. In this case, what you would be doing is you'd be going to a charged state and then collecting the data at 3 different elemental edges and then moving to the next stage and so on. So you'd be doing this kind of stepwise charging of the battery. This work is very much analogous to the JAX paper I had referenced from Mali and others. And it comes much later than what they did. So they did the original work, but this paper did 1 or 2 things in addition to what that JAX paper talked about, and that is we also looked at the relationship between the structure and the crystal field splitting that we could pick up from the manganese T2G and EG bands, as well as the actually measured the magnetic properties. So there was also a parallel study of magnetic properties on these materials. So one of the things to point out here is that you can follow the shifts in the Zane's features using some kind of a scheme, and that scheme has to be somewhat physically relevant. This is mostly for the benefit of the students who are watching this presentation. So if you use some scheme and you're consistent, you may think that because you're consistent in the way you are applying your scheme, you would be getting meaningful information. But you can see that also is not necessarily going to give you the same information depending on the type of scheme. So here, if you take the half edge, the half point of the white line jump or the jump itself, and use that as the position, you get one set of trends between nickel, cobalt, and manganese. And on the other hand, if you take the white line inflection point, and then you get another trend. So going by the one on the left, it appears that nickel is doing all the oxidation throughout this charging of the battery, and cobalt and manganese are non-participants. But not only that, but something strange that appears to happen is that manganese actually shifts in the opposite direction a little bit using this criterion, and you may misinterpret that as manganese getting reduced while while you're charging the battery, and that doesn't quite make sense. On the other hand, if you follow the inflection point, then you see that they all move to the right, and that makes a little bit more sense. If for nothing else, then the fact that these are this is a solid solution, and you have whatever is happening in the nickel area would indirectly affect what's happening in the cobalt and the manganese area, and so if you have basically shrinking of the lattice, for example, and that shrinking of the lattice or expansion of the lattice, that would change the average bond distances. And as the average bond distance changes, there should be a similar trend in the shifts. So the one on the right is the more accurate one, but then you can do an 1/r² correction to get a better understanding of which of these three are actually chemical changes versus just structural changes. When you focus on the manganese happens to have a partially filled T2G and an empty EG, and so we were able to get both of the, I believe that's true, partially filled or partially filled throughout. I think it's in any case we have the ability, we have empty states in both T2G and EG for manganese, but that but in the case of cobalt and nickel, the T2G is filled, and so we are not able to see the T2G. We only see the EG. In the case of manganese, we see both, and therefore we can use the centroid positions of these to kind of map how the crystal field splitting changes as a function of de-lithiation. So we try to use this as a proxy for the entire structure. We don't have a direct measurement of the crystal field splitting from the nickel and cobalt point of view, but we're trying to use the manganese as a guide. So here is a look at another. So let me describe what we're seeing here. So on the left is that trend that we're talking about in terms of percentage de-lithiation, and it's looking at the crystal field splitting. And on the right, we have some magnetic measurements. The one on the top, we can ignore. That is basically temperature dependence and of the susceptibility. And so that is being fitted to the Curie-Weiss law. So it's another aspect to this. But the one on the bottom is showing the change in the magnetic moment as a function of in this case, lithiation, because you're going from left to right, you're actually adding lithium into the NMC compound. So one unfortunate thing in trying to compare the figure on the right to the figure on the left is that the axes are reversed. The one on the left is the percent de-lithiation, and the one on the right is percent lithiation. And so now we have to kind of try to see if we can take the mirror image and look over. So I will do that. I will take the mirror image of the one on the bottom here and flip it on and overlay it with the correct scaling. So let's do that. So now we are plotting them on top of each other, and we can see that if you take the mirror image of a label like this, x equals 0.5, it becomes x equals something that looks like 2.0. So the mirror image of this actually works as a reciprocal mathematically. That's a nice little detail. And then not to be facetious now, to come back to the science, if you look at the trend of the de-lithiation and crystal field splitting, the original plot, together with the magnetic moment, you see that there's a trend that is similar. So this downward trend here of the magnetic moment as we delithiate sort of makes sense from the point of view of the electronic structure, in that you are removing unpaired electrons as you're oxidizing the cations. And so there's an average downward trend. But then there's a little uptick in the magnetic moment. So the one, what I should have said actually, this is all from the paper, one of the papers that I highlighted at the beginning. But if you see what you should be following is this purple set of data. That's from the electrochemically delithiated compounds, whereas the one in green is from chemically delithiated, and the upper two are models. So anyway, the one in the purple shows that this trend, which we can explain in terms of removing unpaired spins as we oxidize, but then it goes up again, and this upward trend is something that was unexplained at that time, and we kind of made the conjecture that this could be due to the some role that oxygen is playing. So what we had decided, what we were able to say at that time is that when we accounted for all the charge that was removed based on the mechanism of what we were seeing was happening, we only saw nickel participating in the oxidation in a direct way from the Zanes, and the nickel oxidation did not account for all the charge removal. So we essentially had about 39 milliampere per gram that was unexplained, and that led us to believe that oxygen was involved with that. So we can take a break here, and Mali,
So,
are you there?
yes, Faisal,
Yes.
I don't see any questions in the chat so far.
Okay.
So I would suggest keep go to your next topic, and we'll go from there.
And you don't have to stop sharing your screen to take questions.
I don't have to stop sharing the screen. Okay, sorry. Yes, I should have realized that. Okay, going back to sharing and full screen or presentation mode. Okay, so we go to now the other case study. Mali cautions me against using this study by Kava and Hertz, and I think I know why, because their interpretation is kind of strange for what they observe, but I'm using it to show what was actually observed in the magnetic moment transition in lithium cobalt oxide. So I believe that their data is not wrong, it's just that their interpretation is a little bit strange. But anyway, what they observed was that as you chemically delithiate, now again our axis is going, if you think in terms of the battery, we would be going from right to left as you delithiate. So you start with the pristine compound on the right-hand side, and the moment you start to kind of remove lithium, there seems to be a transition to high spin cobalt 4+. Taking that at face value, then the question that you could have is, why would that then go back to a low spin cobalt 4+? What is causing in the initial transition, and then what's causing that second transition? So the local symmetry around cobalt in this system is octahedral, and this is a figure that I generously or casually, I should say, borrowed from Dario. I don't know if Dario is watching this presentation. Dario Arena, thank you for this. So he basically put together a set of conditions that would essentially change. You know, these are some of the ways in which you could change the crystal field splitting that you would find in an octahedral compound, and you can see that it can be susceptible to a bunch of things, including stress, mechanical stress, and changes in the electronic structure directly, including things like an oxygen vacancy. So what we decided to do was to make a study out of this. So this is a little bit anachronistic in that we learned a few things afterwards, and then we revisit some data later. So there was the hard X-ray lithium cobalt oxide experiment that was a set of experiments that was done back in 2004, and we published in 2005. But then later we did some soft X-ray experiments on the oxygen K edge, and much of that was triggered by our ideas of what is causing these effects that were observed. So we made a battery, and Mali will have seen this slide many times before, and he's probably shaking his head. This is a battery that was made using solid electrolyte, so that we could essentially have we could look at the oxygen K edge without having any attenuation through the packaging of the battery. So initially we were trying to, and then Mali and I and Jim McBreen and others, we were sitting around and discussing how to look at oxygen directly while the battery is charging. And our initial ideas were to try and use and actually replicate a liquid electrolyte battery and have a window thin enough to be able to do so. After a few failed experiments, we just stopped because it was a little bit too difficult to try and get a thin silicon nitride, which is the best candidate silicon nitride windowed cell that would still have liquid electrolyte in it and be able to look at oxygen K edge. So later, one of my students essentially was charged with trying to come up with an alternative way of doing this. And he went in the direction of a glassy electrolyte, which had sufficient conductivity, lithium conductivity, to be able to make a solid state battery. So now solid state batteries are also pretty popular, but we made one way back then. This would have been around 2008, 2009 period. But it was not for the purpose of making a solid state battery the best type of battery, or any pushing the extent of the battery itself, but rather just as a means to study the solid state reaction that's happening in the cathode material. So we made this pill that had the liquid electrolyte in between, and then painted composite electrodes on either side. And that was able to be charged and discharged inside a vacuum chamber. And so we were able to measure oxygen directly. Sorry, this is now going back to the hard X-ray stuff first. So I didn't draw a schematic for the hard X-ray in-situ battery because I'm sure you all can imagine what that would be. Essentially, it would be either a pouch cell or a windowed any kind of windowed cell, and lots of people have done this stuff. So it's not really that novel. The hard X-rays are fairly forgiving, and you can essentially pass through a well-designed battery and do transmission X-ray absorption with no problem. So this is the result of one of these types of studies. We were looking at the changes in the cobalt nearest neighbor as a function of oxidation and reduction. So we were charging, resting, and discharging, and you can see here's the schematic of the local structure, and we can see a kind of an expansion and contraction of the second layer as we charge and discharge. But within the layer, basically, it's fairly, you don't see that breathing, and that's because the bonds within the layer are stiffer, a lot stiffer, and then in between the layers, there's a lot more give. So this is kind of something that was already observed using diffraction. So this is not novel. What we decided to do was to look at this entire data set using PCA. So the principal component analysis in this case was in order for us to kind of have an intuition as to whether or not there are just two components or whether there's more than two components. And to the extent that there's at least a third component, then that would mean that we could be involving another reaction and not just the reaction where cobalt is oxidized from cobalt 3+ to 4+. So if we found another species that was necessary for the reconstruction of all the data, then we would know that there's another reaction that's happening as well. And so it would be a kind of an objective clue that there's something other than cobalt that is participating. And indeed, we found that there were three components necessary, and that third component, we didn't know what it was, but we knew that it wasn't a simple cobalt oxidation reaction. So then we looked at we deconstructed the R-space data, and we can just follow that along, for example, just the nearest neighbor positions. That's a nice way of looking at it. And if you look at the nearest neighbor positions for cobalt, then what you see is that they're initially the cobalt oxygen neighbors, which would be the ones down here, split. And then they seem to recombine into a single neighbor. And that splitting difference, the difference between the cobalt oxygen bond distances, corresponds with that of the size difference between the oxygen 1- and oxygen 2- species, according to the Pauling ionic radii. That transition that happens where you see the splitting up until 25% de-lithiation and then recombination seem to correspond with the quadrupolar transition, the pre-edge peak here. When we zoom in, we seem to see, and it'll be clearer when we look at it here. You can see that there's one transition that is happening that is pre-25% and beyond 25% that is fairly clear. And so we can see that our idea at that time was that, yeah, actually oxygen is involved in the initial part of de-lithiation, charge compensation during de-lithiation, and then later cobalt, it's a tandem thing, and then cobalt essentially formally takes over after that. But we didn't have a direct measurement of this. So there's that sudden transition in going from 25% to 37%. Anyway, so now the soft X-ray part of this, so coming back to this battery, solid state battery, there it is inside the chamber, and this is what the schematic looks like. This is what it looked like inside. And we did the battery cycling, and lots of the little things are happening, but one thing that we can see through the difference is that there is density, the new unoccupied densities of state that are coming into play as we charge the battery. In the same region of up to 25%, we looked at the L edge for the L3 edge for the cobalt, and we see essentially no change. And so there doesn't seem to be any d electron hole formation in that initial 25%, and oxygen seemed to be doing all the work. So this might be a good place to stop. But let me just say that as a sanity check, we did a battery. We made the NMC battery solid state, and then we looked at the nickel, and the nickel essentially does change as we transition. So in this case, we are seeing the changes that we expect to see, but cobalt doesn't change. All right, so let me stop at this point, and we'll pick up from this next part. So let me stop for questions.
Faisal?
Yes.
We have a bunch of questions. The first one is from Divash Dakal, and he or she is interested in knowing, since you have multiple transition metals, is it a concern for the needed step height at the edge? I presume this is referring to the NMC compound.
I have to interpret a bit. So if you're hearing your question and you want to step in, please do so over the mic. But my interpretation of your question is that you're referring to the hard X-ray data, because that's what I presented so far for the NMC.
Yes, I was referring to that.
And in that case, you're asking whether or not step edge differences are a concern. Well, one thing you have to always do is, as a part of course, is to normalize the step edge. It's a part of the analysis of an interpretation of what you see, and without normalization, you can have lots of problems. So you normalize the step edge height to the step edge to be a unit transition. So you are always comparing on a per atom basis. I don't know if that was the part of the question, or was it something beyond that you were asking?
Jerry, you want to ask your question?
Sure, I can do that. I was curious, when you're doing the soft X-ray measurements on the battery materials, do you have any problems with self-absorption, and do you need to use inverse partial fluorescence yield?
There's going to be self-absorption if you use fluorescence yield, because the amount of the transition metal is significant. Since we were essentially looking for and also for the oxygen, that would be the case. Since we were looking for qualitative changes, we were not too concerned about it at the moment. If we were trying to quantify things, then I guess we'd have to take further steps to address the self-absorption issue.
Okay, thank you.
So there's another question from Jean. Jean, can you ask your question over the phone, microphone?
Yeah, I can. Yeah, thank you. Hi, nice presentation. So I'm a postdoc, a researcher, and I'm working in sodium-ion batteries. And I see that you developed a solid electrolyte for lithium. Do you recommend a sodium solid electrolyte for sodium-ion batteries? Does one exist?
I am not up to date with all the latest on solid electrolytes for sodium compounds, especially. I imagine that there should be. We used a chalcogenide glass, and chalcogenide glass system are with various alkali ions are possible. So I don't see why it wouldn't be possible. Now there may be other issues that would prevent you, chemically speaking or physically speaking, from using them. Maybe Mali knows something. Do you have a comment on this, Mali, about sodium solid state electrolytes?
I'm fairly sure there are solid electrolytes for sodium conduction.
Right.
I don't work exactly in that field, so I do not know.
So I would hesitate to say something about this as well. Mali, the gentleman in Iowa State, what's his name? Works a lot on alkali glass. I forget his name. He's in the chemistry department, I believe, in Iowa State. His name is escaping me. He's a chemist. You might want to contact him. I'm sorry, I don't remember his name, but if you look at chalcogenide glass in Iowa State, you'll probably run into his name.
Okay, yeah.
Sorry?
I will. I said, yeah, I will. Thank you.
Yes.
Oh, okay. Thank you. Thank you, Jerry. Perfect. Thank you. Nice talk.
So there was a question from Yang Ha, and basically saying that you were jumping a bit too fast with the PCA slides and would like to get the reference for it.
That PCA work is a part of the lithium cobalt oxide thin film battery reference that I had. So if I may go back to my first slide or second slide. So this paper here has the PCA work.
Yeah, it's a little hard to see that the
Oh,
citation.
it's hard to see that. Okay, it was one of the references that was on the announcement. Is the first paper on the announcement. So when you go to the abstract and announcement, you'll find that paper. So are there other questions?
So there is another question regarding beam damage. What about the effects of beam damage?
Yeah, I don't know. The beam damage is an issue in these oxide materials. At least on the hard X-ray side, we didn't ever see anything that we didn't ever see anything that was significant. And I think Mali, you'll agree with that, right? Because
not in a bending magnet, yeah.
Yeah, and a bending magnet beam line. But on the soft X-ray side, you do run more of a risk for beam damage. I think the beam damage would happen more on the electrolytes. If you have liquid electrolytes, let's say that beam damage certainly will affect the liquid electrolyte, and so it may affect the reactions that are happening near the surface of those electrode materials. And so like the SEI formation reaction could be affected, and that may indirectly affect your understanding of what's happening. So you have to kind of probably do an experiment or two to standardize your understanding of the beam damage effect.
Great,
So
Faisal, continue with your talk.
Yeah, okay. So one more example, just we wanted to, so speaking of electrolytes, we wanted to see whether or not if we remove the electrolyte and looked at a material that lends itself to being formed in a thin film geometry with a high degree of texturing, whether or not we could use that as a proxy for what is happening in when we lithiate and delithiate. So here we took a sister Delafossite compound, lithium niobate, which can be used as a battery cathode or battery electrode. But you can see because of niobium, the weight of niobium, it's not going to give you a high energy density, but it has a high conductivity. Just as an aside, it does have a high electrical conductivity, so it does provide a good alternative for micro batteries or thin film batteries without one which doesn't require it doesn't require any carbon black or any kind of electronic part of the composite that carries the electronic charge. So So it's really good on the side for when you're considering thin film batteries. So anyway, the lithium niobate happens to also have these memristive properties, which we were looking at with my colleague at Georgia Tech, Alan Doolittle. What we did is we just made a thin film battery, a thin film deposited on a substrate, and essentially laterally polarized that and tried to create a lithium concentration gradient, and directly looked at the oxygen K edge to see whether we can follow a spatial gradient in the electronic structure of the oxygen K edge. So here's a little bit of a closer look at that. So you could see that going from one end of that piece to the other end of that piece, you can see the number of empty states in the oxygen relative to the starting condition does change. And so you can kind of take the difference and interpret that as from the point of view of the hybridized orbitals with niobium. So we were able to show that oxygen can be very sensitive to the lithium concentration, and that lithium concentration gradient can be created without having a battery type of geometry. You can actually do it more from the point of view of an electronic material. So that's kind of what we were trying to do there. So coming back to this charge compensation thing, I want to just tie the things up. So going back to this idea that these magnetic measurements showed, the thing that was missing from that picture was what is causing the transitions in the first place. And since we see, going back one step here, that there is an initial presence of oxygen holes, but then that appears to go away, and then we kind of end up with the oxygen 2- species back again. That seems to suggest that initially you have a presence of these oxygen 1- species as the ligand in these octahedral geometries. And then once the tandem part of the reaction takes over, where cobalt takes over, it reverts back and essentially goes back to its original state, which is still puzzling to me from a chemical point of view, but this is what the data at least is showing. And it corresponds very well with this reversal of from the high spin back to low spin again. So this high spin back to low spin, that is the part that we were not able to quite reconcile before physically, like why would it do that? And if you have a ligand that essentially transitions from 2- to 1- and then reverts back again, that could change the crystal field splitting in the right way to cause this transition initially and then back again. So that's kind of what we are trying to correlate. We're trying to see that that de-lithiation essentially can be used to trigger a spin transition, low spin to high spin, and then back again to low spin. Again, you have to think of this plot in reverse scale to this plot here, and so we see we're seeing the low spin to high spin transition happening here, and then back to low spin again here. So I just want to conclude by saying that if you can, try to design experiments where you take advantage of soft X-rays. Try to think through the kinds of things you are actually trying to measure and what it is that each of those energy regimes will give you. So there is always a trade-off, and so you should try to do as many different things that complement each other. So in this case, we demonstrated that if you use a solid electrolyte, you can actually use that to look at the solid state reactions within the cathode materials without having to worry about the vapor pressure of a liquid electrolyte in a high vacuum chamber. And I think this was the first time that an in-situ or operando battery showed oxygen activity. So I will stand by that unless somebody corrects me. But as I said, others had conjectured, in fact, that Jack's paper that I referenced was referencing another paper prior to that, where there were already ideas of oxygen electron holes and oxygen sites, and there were some ex-situ experiments already done to confirm some of these ideas, and there were also some theory work that had been done on that. But as I said, the Operando experiments helped to confirm a lot of these initial ideas. So I'll stop there.
Thank you, Faisal, for a wonderful talk. There has not been any additional questions. There was a comment by Kent Griffith, not to underestimate the niobium battery because it can give a 2-electron redox process.
Yeah. Mm-hmm. Thank you. I can stop sharing. Okay.
I don't know if Jerry is online.
I'm here. Sorry. Yeah, I wanted to thank you, Faisal. That was wonderful. I guess I did have one question, which is, in what other systems is it believed that the oxygen plays such a potentially important role in the redox?
You mean from the battery point of view?
Sure. For example.
Well, I've been hyper focused on these layered compounds, and that's kind of been my thing. And they had in commercial success as batteries from the beginning, and they were starting to be incorporated into commercial applications like the Sony batteries, and then the Samsung batteries later, and of course also on the Boeing 767 Dreamliners. So in all cases, these were related compounds, and there were all these incidents of unexplained reactions that seem to just be triggered, and you had these kind of explosions where batteries would catch fire on their own. I always felt, maybe it was a self-serving for me, that it's possible that these reactions happened from the inside of the battery without any puncture or any need for oxygen from the outside, that there's plenty of oxygen inside, and basically you just have to bring the oxygen close enough to its atomic state or 1- state, and it becomes much more mobile, and it goes to a hot spot, and in the presence of an electrolyte that can burn, you can basically have all the ingredients for an internal fire. So that's kind of what I know does have oxygen involvement. Then later we were focused on this niobate material, initially mainly for its memristive properties, and we're trying to use oxygen as a way of triggering these kinds of memory storage potentially, and so kind of having more of an analog circuit. These are the ideas we were thinking about. So I have been mostly stuck on the the LiMO2 layered compounds. I know that oxygen is less of a concern for some of the other, like the phosphate batteries. I think is less of a concern. Is that true, Mali?
Yes. Just to add, Faisal, Jerry, there is a class of materials called as lithium XAS materials.
Yeah.
Where the charge compensation process is not just from the covalency of the metal-oxygen bond, but might involve the lithium-oxygen-lithium linkages, where there is no hybridization with the transition metal.
More ionic, basically. Yeah.
So there is probably more of an oxygen involvement directly rather than a hybridization that comes in between.
I see what you're saying. Okay.
So there's a lot of work in that area.
Okay. We've got a potentially related question from Kent Griffith. Kent, is your mic available?
Yep. Thanks for the really nice talk, Faisal. I had a question about the NMC charge compensation mechanism that you presented. So I didn't quite catch it from, you showed the different ways of interpreting the changes across all three transition metal edges. Could you sort of summarize what the
Yeah.
conclusion or state of that work is now in terms of, because I know there's been a lot of debate about whether manganese plays any role or if it's only certain concentrations of NMC where the different metals are playing active roles versus passive roles?
In the compound that we studied, we found manganese not to have any direct role that we could measure. And even more to the point, cobalt seemed to have, if anything, a late involvement in the charge compensation reaction that would be above 50% de-lithiation. So that's kind of the nominal conclusion that we were able to come up with at that time. So most of the charge compensation from the transition metal point of view was happening because of the nickel, and the excess amount of charge compensation was at that time ascribed to some involvement with oxygen. Now, what we tend to believe now is that that oxygen is the oxygen that is tied to the cobalt. So if I was to make a bet, my bet would be on nickel doing most of the work, oxygen that is neighboring cobalt, local to cobalt doing a fraction of the work as well. Mali, I'm sure will have something interesting to say on this. Mali, what do you think?
I think I would agree with you.
Yeah.
Okay,
and
thanks.
things change, of course, if you change the proportions of nickel to manganese, and of course, if you over-lithiate, like Mali had just talked about, that changes the overall story. So I don't know. I'm giving a wishy-washy answer, but at least in our study, we found that nickel and oxygen do the work.
Okay, thank you.